in this example, we are going to see some more cases in which we can obtain a minimum expression for some logic functions. We have already seen in previous examples everything we see here, but it's just to sum up. The idea and what's important of Boolean algebra when used to design digital circuits is that Boolean algebra gives us a tool to simplify expressions, to obtain minimum or minimal expressions. From those minimal expressions, we hopefully can build circuits that are more simple, that are easier to fabricate. So this is the whole idea. So that's why we need to simplify these functions no matter how they are given to us. So in this example, we'll see how to minimize different functions given in different ways, or have already been covered by previous examples. But I will do it here as additional as an additional exercise. So basically, we want to obtain the minimal sum of products and product of sums for functions given in different ways. In the first case, we have this. This is a function here of 3 variables. And another point that students tend to make mistakes is that they tend to think that variables are always named A, B, and C, maybe because professors tend to use all the time the same names for the examples. So this time I'm going to change these names. Okay, let's forget about those, and let's consider function is a function of slightly different letters X, Y, and Z, for example. Okay. In this case, I'll draw my kernel map. This is a 3 variables kernel map. This is something like this. Three variables. Now, it's important to know the name of the function below the map, the variables in the right order. Okay. The values sorted. In the right way, 0, 1. Okay. Now, because these are minterms are 0, 1, 2, 3, 4, 5, 6, 7. Okay, that's 0. You have minterm 1, 0, 1, 2, 3, 4, and 5. So these are the ones, and these are the zeros. I'm going to put the zeros and the ones in the same map. I'm going to use the same map to do the sum of product and the product of sum. I don't really recommend it. I recommend to draw a new map for every operation, but except if the map is not very complicated and you have the option to use different colors. Okay, so here we will use the green to minimize this. So I have this one and this one. This is an implicant. I don't have the corresponding adjacency, so this will be a prime implicant. With this one, I can also form this prime implicant. With these two ones, I form this prime implicant. This one together with this, I have this prime implicant. Okay. And because it's not very complex function, I just can write it right away. So this is f could be equal to, this one is the one when x is 0 and z is 1, x z plus this one here will be I complement z. This vertical one will be x complement y, and this one here is x y complement. Okay, this is a simple exercise. Now for the zeros, I have this one is an isolated term with no adjacent zeros, and this is another isolated term, so the expression as a product of sums will be this one when all variables are 0, x plus y plus z. This one, x and y are 1. Okay. So in this case, the product of sums is more simple than the sum of products because it has one term less. Okay. Now, the function can also be given as a product of max terms. So for this function here, we will write four variables, sorry, kernel map. I will change to blue color. And I have this. Now again, I will use different names, okay? Like F, don't know, M, N, P, and Q, right? So there will be M, N, P, and Q. Because different problems may need different names. So you have to get used to use any name that comes from the problem. So this is F. Now, because this is the list of max terms, these are the cases where the function is 0. You also have to know that in this order, because of the order given here, this is min term 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So the rest are ones. And again, I can start with the sum of the sum of products or the product of sums. So I will start with the sum of products. This one here has forms an implicant with this. This one here additionally forms an implicant with the one on the right. Okay. This one and this one are an implicant, and these four are a bigger order implicant. So this is a prime implicant. And I think that's all. Okay. This one is essential. This one is essential. And with these two, I have all the minterms covered. So I don't need the one in the middle. Okay. So in this case, F could be simply this one plus this one. This one is 0, 0, which is M complemented, N complemented, P complemented, plus this one here, which is M is equal to 1, and Q is equal to 1. Okay. Now, as a product of sums, we take the zeros. I'm using the same map by changing the color, and this time I may start with the 0 here, for example, which is a bit isolated. And here, these two are adjacent to these two here. I have a order 2 implicant. The adjacent would be this one or the one here, this 4. So because I don't have those, this is one of my prime implicants. But these two zeros are adjacent to the 2 in the bottom here. So this is another prime implicant. Okay. Now again, this 0 here and this 0 here form an implicant, and these two don't have one in the bottom, but this has this in the top. So this group here is another prime implicant. Also, this 0 has this adjacency. You see that I always do it in steps. I don't see these 4 all together. Okay, yes, they are 1, but I prefer to go one step at a time. This is a minterm and another minterm. Order 1 implicant. Then now I look for another order 1 implicant on the right, on the left, sorry, on the right, on the bottom. So I have this order 1 implicant. This order 2 implicant, sorry. So now this one as well has one on the right. These two have one on the bottom. So this is another prime implicant. I have many of them. This is essential. This is essential. This is essential. And with this one, I covered all these. With this one, I cover all these. Okay. And with this one, I cover the 2 remaining zeros. So just taking the 3 essential terms is enough to cover the whole function. So the expression for this is m is equal to 0 plus p, which is equal to 1. Now, this vertical one is m is equal to 0 plus n, which is equal to 1. And this one here, these two and these two. Here I have m is equal to 1 plus, and here q is equal to 0. So that's it. Minimum expression. So this is the first example. We derive the minimum expression for the list from the list of minterms. Okay. Normally, if we are doing a real problem, we normally end up with a truth table. Okay. So actually, going from the truth table to the list of minterms, that could be cases where the function is 1. Okay, this is case 0, 1, 2, 3, 4, 5, 6, 7. So cases when it's 1 is 2, 3, 5, 6, and 7. So I have the list of minterms. Cases when the function is 0 is 0, 1, 4. So I also have it as a list of maxterms. Okay, so if we have a truth table, I go to the list of minterm and maxterms, and from here I can go to the kernel map and do this simplification. But more often you can simply go directly to the kernel map from the truth table, because actually it's very straightforward. Yes, to go directly to the kernel map. You just copy the values in the truth table. If you, depending on the sorting, but if you use the conventional sorting I'm using all the time, it means that you fill this kernel map in this case, starting here, going here, going here, going here, then going here, 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 and here. Okay, so if you follow that path, this is 0, 1, 2, 3, 4, 5, 6, 7, you can quickly move the information from here to the kernel map directly, or from the list to the kernel map. directly, okay? So I would say, going directly from the truth table, I would say 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, okay? So actually this is min term 0, 2, 3, 5, 6, and 7, or max terms 0, 1, and 4. Okay, and now from here I just could simply obtain the minimum expression. Okay, this is very simple. Like in the first case, these are my two prime implicants. I'll make some room here. And this one is B, simply B, plus, and this one is AC. Okay? And using max terms, this is one implicant, this is another implicant. So this would be A plus B, this one here, and this will be B plus C. Okay, the first one is a bit more simple. Now, the last example is what happens if I have to go from any expression, not the sum of product, nor a product of sum, to simplify this expression. We already know how to do it. If you remember in previous examples, we simply may go from this general expression by doing the distributive axiom, distributive theorem. We can go to a sum of products, which is a normalized form. Okay, and from the sum of products is easy to go to the key map. Or I can go to a product of sums and then to the key map. Okay, a longer option could be to draw my key map. I'll do it here. And as I say, a much longer and more error-prone method would be to calculate the function by substituting the values for every possible place in the K-map. Okay, I don't recommend that. I mean, you can A, B, C, D. And we may try substituting here. Okay, this case will be 0, 0, 0, 0. I'll say it's 0 plus 0, 1 complemented, 1 plus 0 is 1 complemented, so it's a 0. This with all this is a 0, and then it's 0. It could be 1, 1, 0, it's a 0 complemented, it's a 1. So in this case I think it's a 1. Okay, I'm not writing it down, I do it by heart, and I think it's a 1, so I may now substitute all these values here, calculate again. But it's a very time-consuming, very boring, and error-prone. So it's always better to go to a standard normalized form, okay, as we have done in previous example. If you remember, we simply take our expression and yes, we try to find a normalized form, not minimal. When it's normalized, it's easier to minimize using the Kahneman. So as we have already done in other examples, we start by simplifying. We apply De Morgan, could be a complement. Change the order with the N, B. Now we have A, C plus D. Okay, now we have plus, and this would be De Morgan here again. Okay, this would be B, C, all the this could be B or C, all complemented. or this and becomes an or, all this complemented. B complement plus D complement. You can skip the parentheses because the complement does the job of the parentheses here. So continue our simplification. Now we apply distributive property anytime we can. This time this will be 0 because it's A times A complemented. Will go away and I have a complemented B D plus this will be B complemented C complemented plus this would be B complemented twice would be B, and this would be D complemented. That's it. Now that it's a sum of product, it's very easy to move to the kernel map. I don't know if it's a minimal expression or not. Maybe it's already minimal, but we don't really know for sure. So we can move it to the kernel map. This term is the term that is 1 when A is 0, B is 1, D is 1. So I find the places here. A is 0, B is 1, this column, and D is 1. So this is this term here. This is 1 when B is 0 and C is 0. So B is 0 is these two columns and C 0 is these two rows. So these 4 cases. We were right, this one was 1, okay? But in one step we find many ones of the function. And now this is 1 when B is 1 and D is 0. B1 is these two columns and this 0 is this row and this row, okay? So we first go to the sum of product. From the sum of product we can go to the kernel map. And now we can do the minimization as we have done before. All this is a prime implicant, okay? These 4 are also a prime implicant. This column is also a prime implicant. These two with these two are also prime implicant. And these two together with these two are also prime implicant, and I think that's all, okay? This is essential, this is essential, this is essential. And with all those essential prime implicants, I have covered these ones. I don't have it covered yet these ones here. We can cover them with this one or this one. The two options are implicants of the same order. We can choose any of them, okay? I decide to use this one here, okay? The one that here. So our function could be this one is A complemented, C complemented, or this one is B complemented, C complemented, or, and the one on top at the bottom could be B D complemented, okay? So this is rightly one of the minimal solutions, okay? Not the only option, but the other alternative is as good as this one. As you see, we have simplified it a bit more, okay? From here to here. This term has been simplified. Instead of using this term, we have changed by this other term, okay? Giving, hopefully, if no mistakes happen, the same solution. Now, the same thing can be done for the product of sums. If we consider the zeros, this is a prime implicant here. This is another prime implicant, and this is another prime implicant. This is essential, this is essential, these are the only two we really need. So in this case we have these two are A complemented plus B complemented plus D complemented, and this one here on the sides is B plus C complemented. Okay, so this rather, this rather long example, okay, we have seen that no matter what the origin of my function is, midterms, no matter what the original representation of my function, no matter if it's normalized or not, we now have the tools, especially if my function is simple, up to 4 variables, this very rather easy to use tool, the kernel map, to find the minimal expressions for my function. And with the minimal expression, now I can go to obtain a good circuit that implements my function and solves my problem. Thank you.